Something that came up in our last videos was this idea of getting closer and closer to a point, but not equaling it. And that is the idea of a limit. So in this section, we're going to talk about this limit notation, the idea of limits, and also how to evaluate limits. So if we can make the values of f of x arbitrarily close to a number L by taking x to be sufficiently close to a number A, so we're getting closer and closer, but not equal to, we write it in this format here. So our notation, this is for limit. So we have the limit of f of x as x approaches A is equal to L. So on the left-hand side of this equation, what we're getting at is we're describing what's happening with x and then what function we're using. So I think of the left-hand side as telling me what's happening with x, and then our output on the right-hand side, this is typically what's happening with y. So it's the idea of our limit is going to be a value on the y-axis, and it's what our function is approaching as x is getting closer and closer to A. So the limit of f of x as x approaches A is equal to L. Let's take a look at what that means in terms of a graph. So we have this graph below here, and we're going to evaluate a few different limits. So this first one, limit of f of x as x approaches 1. So I'm really focusing on is this as x approaches 1, and we're going to be doing this from either side. So it's like if I'm at x equals 1, I want to get closer and closer to x equals 1, kind of pinching in around it. And where I'm doing this is on the function. So if I go to the actual function, the idea is what's happening as we get closer and closer to that point from the left-hand side and from the right-hand side. Now, in this case, that point is defined, so it's fairly straightforward. And the solution that we want is to map to the y-axis and get our y value out. So what this is showing me is that as x approaches 1, f of x is getting closer and closer to 2. And that value of 2 right there, that's our limit. So this limit, where did it go? There it is. The limit of f of x as x approaches 1 is equal to 2, because that's the y coordinate that we're getting closer and closer to. So it's this squeezing around of the point. So now let's look at what's happening as x approaches 2. And what we're going to do is it's an undefined point, so we have this hole in the graph, but the idea of limit is that we're just getting closer and closer to the point. It's not about being equal to. And you can imagine, like, say you and your friend are walking here. It's like you're walking to the point from the left-hand side, your friend's walking to that point from the right-hand side. Where would you meet up? And it's maybe not at an exact spot. You can't stand at the same exact spot. But what's the spot that would be in between you, essentially? So we are focusing on this, and it doesn't matter that we're undefined there. It's this idea as x approaches 2, our function approaches, and approaches is such a key term here, because it's this idea of getting closer and closer. And what we would do is we'd want to map to where are we landing on the y-axis there? What would be the y-coordinate there, even though it's undefined? And what we would see is a y-coordinate of 3. So our function's getting closer and closer to 3 as x is getting closer and closer to 2. So that limit as x approaches 2 for our function would be equal to 3. Then the limit as x approaches 3. So with this one, we just have all the different scenarios in this graph here. It's perfect. So we have a removable discontinuity here. Ooh, it's just a term we'll talk about more later on in the next week. So we have a hole in the graph, but we are defined elsewhere. But again, in terms of approaching 3, like we're walking along this path over on the left-hand side, we're walking along this path along the right-hand side, what are we getting closer and closer to? So that coordinate that's defined up above doesn't matter at all, because we're not approaching that point. It's just happening elsewhere. So that point, we can pretty much ignore it. It's important in terms of definition, like our function is defined there, but in the terms of limit, it isn't helping us. So really what we're focusing on is the hole in the graph there, because that's what we would be getting closer and closer to as we approached it. So as x approaches 3, our function is approaching, and then again we want that y value. So we just map to the y-axis, and it would be that same value of 2. Oops, not that. All right, 2. So the limit of f of x as x approaches 3 would be 2. So those are kind of our 3 scenarios with coordinates, if it's defined, or there's a hole but it's defined elsewhere. But it's this idea of they're all somewhat treated the same, because the idea of getting closer and closer, it isn't about what's happening at that exact point, it's about what's happening around that point. And what we'll think about, and what we'll see down below too, is we're kind of thinking of a table of values of what are the y coordinates approaching from the left and from the right, and where would they meet up if we didn't evaluate what was happening at that exact coordinate. Okay, our last scenario here, so limit as x approaches 4. So say we did that kind of walking scenario, where you're walking from the left-hand side, your friend's walking from, I think I messed up my directions, from the left-hand side, your friend's walking from the right-hand side. So we're saying as x approaches 4, f of x is approaching. Well, I'm all the way up here, my friend is all the way down there. We're not meeting up. We didn't meet up somewhere. So our function isn't approaching a single point. So since it's not meeting up, what we say here is that the limit does not exist. So we didn't meet up at the same spot. So with this, we would just write D and E for does not exist. So they should line up to meet at the same point. In the next video, we'll talk about how we can just approach from the left or just the right, but these are two-sided limits where we're approaching from both sides. So that's where I was drawing the arrows from both directions. And when they match up, it's that y coordinate that would be our solution. If they don't match up, then we say does not exist. Okay, let's look at another scenario here, which we could evaluate this from the graph itself, but I kind of want to talk about the idea of our tables. So if we have this rational function, and what I want to do is evaluate the limit of that function as x approaches 4, we could do this with a table where, again, we don't want to evaluate what's happening at exactly 4, because it's all about this idea of getting closer and closer to 4 from both sides. So with that, we can set up our table so that we're starting at 3.5, and then it's getting closer and closer to 4. And then over here, we're just a little above 4, and then we kind of move away from it. But what we want to know is, where would those be matching up? And I went ahead and set this up in Desmos so that we can see a table of values. So I have my function, and then I have all my outputs here. So it starts at 2, and then it goes 1.33, 1.11, 1.01, 1.001, and then we hop over to 0.999. And what I'm trying to fill in the blank with is, what would be the y value between those? What are we getting closer and closer to? And it looks like we're just skipping over a 1 right there. So I'm interested in here, and I'll just fill in that this was like a 1.001, this was a 0.999. So what's happening right there is that we're skipping over an output of 1. So that's making me think that this limit of our function as x approaches 4 is going to be equal to that output of 1 that we're missing. And we could see that with the graph over here. So we're getting closer and closer to 4 on the left-hand side, on the right-hand side, and where they're meeting up, is that hole in the graph, which is occurring at y equals positive 1. What I like about Desmos with these two finding limits, you can get a good visual of where the coordinates are coming in on our graph. So you can see how they're kind of far away, but then they're getting closer and closer on either side to that value at the hole that's right in between them there. All right, so those are our two-sided limits. Oh, sorry, what if we added a coordinate defined at 4, -5? So what if I went to 4, -5, and I said, but hey, we're defined down here. That's great in terms of our function of, cool, now we're defined at x equals 4. We have an output value. It does not change the limit though. Our limit stays at positive 1 because it's that idea of getting closer and closer from the left and right hand side. So this does not change the limit. Okay, that does it for our two-sided limits. In the next video, we'll talk about one-sided limits.